Hey everyone, so my name is Wang. As has already been mentioned, I'm a solutions architect for Nvidia based in Australia, based out of Melbourne, but I do cover the whole region. So I do recognise a few familiar faces from previous events. Do come and chat to me. I'm the guy sitting next to the really massive computer out there that looks and sounds like a jet engine, so you really can't miss it. Today I'd like to talk to you guys about GPU accelerated deep learning. Most of the examples you'll see are based around image classification, image search, although we have a lot of tools that extend to natural language processing, signals processing, and so forth. So let me just get into the agenda real quick. I'll quickly cover what deep learning is, how that differs from traditional machine learning and not deep, or I guess shallow learning, and then talk a little bit about GPUs. I'll start off maybe with what GPUs are and why they turn out to be fantastic for deep learning. And then finally cover the Nvidia Digits software platform, which is a fairly recent innovation from our labs. So deep learning. Deep learning, as you would very well know, is a subset of the more broadly termed AI, or artificial intelligence. In recent times it's come to the fore because the size of the data problems that we need to analyze, right? You can no longer do it systematically and exhaustively. So you really need something a lot more specialized to mine through all the data. And it just turns out that this special class of machine learning, deep learning, is fantastic for this, and more so they're fantastic for the GPU architecture. Both the software tools that we've had in place for a number of years now, and also the underlying hardware, many cores, thousands of parallel processing cores. And as I mentioned, the focus to date, or the many successes which you've seen in the media, have been around these perceptual, visual perception-based tasks. So image recognition, controlling sort of video games. Got a quick video about that. And a lot of the large internet search companies, obviously with their visual-based search, voice-based search, are really getting into the R&D for obvious reasons. A few practical examples of deep learning. Again, no surprise here that you'll see a lot of tasks being performed on visual input, right? So on the top left there, we've got image classification, detection, and maybe semantic labeling of objects within the scene. These are probably comes from a video feed, but if you take individual frames, then the problem decomposes to an image-based one, right? And if you extend that to some of the search engines, speech recognition, engines like Siri, Google Voice, natural language translation, so on-the-go voice recognition and translation, as well as if we extend the video and image capabilities to a more familiar environment, driving around, so autonomous vehicles. You've seen the Google self-driving car. It deploys a lot of GPU-based real-time training, as well as offline, cloud-based augmentation. And more recently, we've seen some development in the biomedicine fields as well. So again, applying the same type of deep analytics, deep learning analytics to MRI data, for example, so volumetric, and we think of that as many slices of 2D data. So the same data processing patterns apply to volumetric CT scans, surfaces generated from those volumetric scans, and so forth. So if we turn our attention back, many decades now, machine learning as a field is really nothing new today. It's been done for a long time and quite successfully in a lot of the scientific and technical fields. But typically, what would happen with these hand-tuned, what's called classifiers, feature extraction is the process. So in the top one, if we're, for example, recognizing staples, you might take dozens of images of a staple from all angles and identify, it's got an edge. It may open up, and that looks like a certain geometric shape. And once you've extracted those features, then you make some fairly simplistic, or in this case, shallow neural net is the term up there, decision whether this is a staple or something else, right? And the point here is that traditionally hand-tuning those feature extraction was a bit of black magic on the side of the data scientist or the machine learning practitioner. So it was very, I guess, a niche thing, and you had to have a lot of training in how to actually code some of those machine learning algorithms to detect those features. And a similar methodology would apply to other signals. So non-image based voice, for example, grams and natural language input, right? So here on the bottom tree there, you're breaking a sentence, which you probably can't read that. The sentence is John fed the numbat, and then we're analyzing sort of John as a name and fed as a verb, and the numbat is a certain construct that may or may not occur next to each other very commonly. But the deep learning approach differs from the traditional machine learning approach in that we use what's called a deep neural network. And so from that pictorial, you can see a lot of these circles, which are called neurons, and they're so named to mimic or to approximate the biological processes in your brain, so the neural connections. And the lines extending between the layers, which are represented as sort of these three-dimensional planes, they process portions of your input data. In this case, typically images, extracting various features, decomposing it, and then reassembling them in ways which give rise to some sort of semantic structure. And so in this case, we feed it, we train it with thousands upon millions of images for which we know what they're supposed to be. So they're labeled, they're called labels. Dog, cat, honey badger in this case. And so there may be tens of thousands of images of a dog at various angles, various breeds, various lighting conditions and so forth. And then we put it through this neural net. At the end, you test against some more images that you have, the algorithm hasn't seen before, and you say, well, did it come up with the right one? And if it did, well, that's great. It means that whatever the connections were being established and how they were weighted was the correct one. If it wasn't, you propagate that error back. And in fact, so what the errors that the algorithm makes during the training stage is what informs the correct connections between those neurons and how you weigh those particular connections between the layers. And the hope is that after we've trained this neural network with millions of images for the categories that that are known to us, if we then feed it an image of something that it's never seen before, and potentially that maybe we've never seen before as well, it will use the training that it's undertaken and give you a prediction within certain probabilistic bounds of what it thinks it is based on the training data. So that's the idea behind deep learning-based image recognition, image classification. More recently, or from large search engine providers like Google, so Jeff Dean, who heads up the deep learning lab within Google, presented at our global GPU technology conference this year, and he got up on the stage and told us about a few of the areas that they're actively working on. The top one is recognition of an object. That's fairly straightforward. Not to say that's a simple task, but in terms of what we want out of an image recognition algorithm, that seems like a fairly straightforward task. And of course, with Google Voice, we can now do voice-based search. And if we put a few of those together, you can augment your search queries in saying, if I ask for a particular type of query and you return a document based on your history of your search behavior and behaviors of perhaps people in your demographic, right, your geographic location and so forth, it might come up with a probability that you'll click a certain link. And so now your Chrome browsers and your tablets and phones can start to pre-cache some of the link content. So for your experience, it looks like it's loading a lot quicker, right? So it'll learn from your behavior what types of results it returns that are more amenable to your tastes, I suppose, and do some sort of smart analytics based on those. Of course, natural language processing, on-the-fly translation, that be quite useful for a lot of people. But what's really interesting is that combining some of their expertise in various image and non-image based search algorithms, Google can now place objects within context within a scene. So if we fed it this image of a baby, cuddling a toy bear, it will actually, of its own accord, come up with the natural language caption, a close-up of a small child holding a stuffed animal. You may not be able to identify what kind of animal it is because you can't really see it, but that's the sort of context that it can now actually generate. And you would have seen, for example, the language person, you would have seen the automatic captioning feature on YouTube, for example. So that's the areas where some of this research is being applied. This is a very quick video demonstration of a company that Google acquired called DeepMind. Their claim to fame was they trained one single neural network to play all the 40 or so Atari games. And after not an inhibitively long time or processing power, the algorithm got so good that it could actually do complete inhuman feats. So you'll see that. So you should count how many times it misses actually. Not very many, I can tell you. And one of the sources about to come, and check out this shot, right? Just like, got you, right? It's pretty incredible. So in fact, it's figured out that it should hide behind the shield, and it fires at the right time. So there are misses, and I think that was the only miss that I counted. And so that's all based on, this is reinforcement learning is a subclass of deep learning, again, where you tell it, hey, here's an image, randomly click left, right, and fire, so there aren't that many inputs, and then this is the death screen, and here's your score. The higher the score, the better it is. Death is bad, right? And then just go. It'll randomly click left, right, and fire, and then it eventually figures out that, hey, if this thing, this enemies are firing at you, and you hide behind the shield, that's a good thing. But it doesn't know it's a good thing, but it knows that it didn't die, 500,000 times out of the million times that it randomly did stuff, so it will do that action more. And for various types of games, the really amazing thing, and the black magic part is, the same neural net learns to play this game versus that bricker game where you bounce the ball and knock down the bricks. And so if you watch that video, it figures out this technique called tunneling. So you create a channel, bounce the ball through, and it sort of reverberates and bounces all in the top part of the screen. And that way it maximizes its score. So it actually does that to an inhuman degree. It's really scary how it can do that. So as I mentioned, neural networks were modeled after, or inspired by, the biological neurons in our brain. They're not a one-to-one representation. We would be God if we knew how to model those. But it's a large collection of what is actually a fairly simplistic connection model, right? So in this diagram, you've got these 3 X neurons feeding into a receptor Y neuron, and their outputs are just weighted by this weight W1, W2, W3, right? And depending, so each of those might be an input. It might be the brightness of a pixel on a screen. So in that Space Invaders game, your location of your pod, may cause some of these things to light up, and depending on the various actions, it'll apply a different weight to how strongly or how weakly that Y neuron should respond, and that Y neuron might be an input left and right, or shoot, or so forth. And so if you string a large number of these together, it turns out that you can mimic very, very complex behavior, complex phenomena, using quite a simplistic model. Because again, our brain doesn't have specific neurons or when we're developing, right? From the embryonic state, there wasn't a million types of neurons, one for recognizing a chair and a dog. They're all visual neurons, and we sort of built up this higher level intelligence with the same underlying, fairly simplistic, by comparison, biological connections. And so that's exactly what artificial neural networks are attempting to do. So some terminology. The input layer is where the input goes in. So think of this as your pixels in your image. The output layer is the prediction: dog, cat, boat, train, so forth. These so-called hidden layers are termed hidden because you don't see them, right? You put something in one end, something comes out the other. You could have a finite but a large number of hidden layers, and how they're connected is quite a complex task. So in this example, let's say you want to train this deep neural net to classify human faces, so recognize the human face, so automatic tagging of photos in Facebook, for example. In the first couple of layers, typically what would happen, it would break this large image into its component very low-level features. So these are segments of boundaries, edges that make up, potentially some of these edges make up the contour of the cheek and so forth. The black dot might be the pupil in the eye. And then as we proceed through the hidden layers, it's the various connections are taking subcomponents of those low-level features, combining them into higher-level features within the face. So a nose, an eye, a chin, and various types of noses. And then as we move through to the final result, the output layer, we're combining those intermediate, mid-level features into higher and higher levels of abstraction. And typically, you train a network on tens of millions, potentially more, images, and the network architecture, I guess, is where all the magic happens. These days, there are on the order of tens of layers, sometimes a lot more. And the parameters are simply those weighting factors and how you connect the various neurons. And so if you do the combinatorics, it turns out that over tens of layers with millions of neurons in each, or tens of thousands to millions of neurons in each, you get billions of parameters, which you have to somehow optimize. And so it turns out GPUs are great for this, and I'll get into a little bit about why that is. Why would you use deep learning algorithms, right? As I already mentioned, it turns out that you do not have to hand tune anything. You string this thing together to say, I think this works well for faces, and you let it run, just like that DeepMind example for games. The algorithm will itself actually discover what the most important features are without you telling it. And you don't necessarily even know how that's not represented in sort of human understandable terms. Certainly it doesn't spit out a plain text saying, hey, this is what I'm looking for. This is how I'm looking for them. There are these intermediate steps which are pretty much how the machine is thinking abstractly. And again, as it turns out that if you deploy a neural net on GPU and standard off-the-shelf server hardware, that same compute power can be used for a multitude of other things. So more traditional rendering, graphics engines, and so forth. And it's fairly scalable. And as I'll show, the Digits platform scales almost linearly with GPUs inside a single server. There's a few more slides going into details about convolutional neural nets here, but again, I won't go into these other than this illustrates that in another example, in this case, not looking for a face, it's breaking the image up into more local areas on the top diagram there, and it's then assembling some of those sub-features into higher and higher level recognizable patterns, right? So in the intermediate features, it doesn't mean much to you, but it's making sense of these angles of lines and geometries and circular patterns, and then as the layers progress, it sort of pieces these things together and say, hey, I see a lot of circular shapes with straight lines, and they're that might be a car. Because a lot of these features occur together when we trained it with the training set in car images. But the point is, we didn't say, hey, car images contain lines and circles and so forth. So as it turns out, in the last decade or half a decade, deep neural nets have come to dominate these vision-based problems. And so why is it so good now? As I already mentioned, the availability of big data has been the key, right? So when it comes to deep learning, and because you need those tens of millions, potentially billions of images to train it, the availability of the database that Facebook, Google, Yahoo have doesn't present a problem to deep neural net training. It's actually the solution. If you don't have enough data, if you don't have enough variety of data to train it, it cannot get very accurate. Whereas if we can see potentially every individual face in the world, then it becomes trivial identifying you out of the crowd, right? And of course, new techniques in the research fields have come a long way. But the biggest explosion came probably in the last few years with the GPUs. So the GPUs were first applied a few years ago, and to date, basically anyone that's commercially competitive have deployed large numbers of GPUs to do that processing. And I'll show you why right now. So ImageNet is it's sort of like the Academy Awards every year of image-based recognition. They provide 1.2 million training images across 1,000 different categories, and you train your algorithm on that. And then they release another set of photos that are secret up until that point, and everyone tests their algorithm and see what is the accuracy that you're able to identify this unseen image set. So through the early 2000s, so forth, it was sort of a steady incremental 2% a year increase because everyone was doing this really long-winded hand tuning, right, of cars and boats and frogs and birds and so forth. But in 2012, a research group out of the University of Toronto deployed GPUs for the first time, and there was like a massive, unprecedented 10% step change in the accuracy. And this was, in this competition, was unprecedented. And since that day, almost every single entry into this ImageNet competition is based on GPUs. So last year, out of 100, I think it was 111, 110 of them were based on GPUs. Only one entry was not based on GPUs. And in fact, between the last time ImageNet was run, which was I believe it was last November, so there's still time to get your entry into the 2015 competition. If you look down there, January 2015, Baidu released it wasn't for ImageNet, but they did it on that data set just because they bettered the result again. And then they were bested by Microsoft and then finally Google. So now it's back to sort of very incremental things, right? Because they've almost hit the limit they're almost perfect. The error rate is less than 5%, which when tested against a human, so a bunch of people sat down and manually tagged 1.2 million images. Turns out the average human accuracy is about 5%. So the computers at the clusters at Baidu, Microsoft, and Google now do better than a human on these 1.2 million images. And so we've seen an explosion in the startup space with all these mostly Silicon Valley and China-based companies. So you pretty much have to be where the data is, right? So they're working very closely with the big search and social media providers. Another cool example here is in 2012, Google released announced the Google Brain Project, where they had a cluster of 1,000 servers watch YouTube for about a week, and it just took screenshots, random screen grabs out of random YouTube clips. It took about 100 million of them, and it turned out to recognize human faces and cats, because they were the two most popular things on YouTube. And that is estimated to have cost them $5 million to stand that server up, and at a running cost of 600 kilowatts for a week. Less than a year later, the Stanford AI lab, led by a few of Nvidia's collaborators and Andrew Ng, who's pretty much a household name in deep learning, they recreated the same experiment using 3 GPU servers, right? And for a cost of $30,000. Today, it's probably the same thing that costs you half that. And for a power bill that you can plug, it's a couple of wall heaters it would take to run that server. So it just shows you how democratized deep learning and image-based classification has come with the advent of GPUs. So, why a GPU is good for this? Well, it turns out that if you look at the underlying maths, certainly something that I'm not an expert at, of deep neural nets, you need something that's inherently parallel. You need very large matrix operations, which consumes a lot of floating point maths. And then you also need the bandwidth. So you need to feed those 100 million images into all those processing cores. It turns out GPU ticks all those boxes. And I guess the column that's not shown here is that computer games, which is what GPUs were born out of, also tick all those boxes, right? You've got to draw millions of pixels. It turns out the lighting and the effects are all matrix-based maths. You obviously need the flops to drive that, and you need to feed it at a very high rate, so you have frame rates. So I'm running a little bit behind on time. So if you come to my talk tomorrow, I'll actually show the next section, which will be a hands-on demonstration of what I've got running in the lobby there, which is our Digits 2.0 platform. So to write any machine learning application, you obviously have to have hardware. These are the GPUs, the servers that they run on. You need drivers, the libraries that you actually have to leverage. And then there's some middleware layers like frameworks, and finally the applications, right? So the speech recognition, the image analysis, and so on. So Nvidia provides or contributes to all of these areas. We don't directly contribute to the frameworks. So the fundamental research in deep learning is done out of the universities and the research labs. What we do is our engineers help their developers, and they can certainly help a lot of you guys in the developer space port some of the key computational elements of your algorithm across the GPUs and get that 10-fold, 50-fold increase in speed. And so cuDNN, CUDA-based deep neural net library, is a building block library which all of these well-known deep learning frameworks such as Caffe, Theano, Torch, if any of you have used those, you'd be familiar with that. So we're seeing about 15 to 20x speed up across popular deep neural net constructs. And this is, by the way, on one GPU. So I've got 4 GPUs, 4 of these running in the box outside. This is on one of those GPUs versus a dual socket 16-core Haswell. Right, so that's where you get your bang for your buck. And all that's doing is you don't have to change your overall software architecture, but you take the most computationally intensive 5% of code, right, and you move that across to the GPU. And that 5% of code was probably consuming 80–90% of your runtime. So that's where you get your 20 times speed up. And so Digits is our attempt to democratize access to deep learning even further. It's a web-based interface that front ends onto these more complex frameworks like Theano, Torch, Caffe. Today we've got Caffe launched, support for Caffe only. Torch and Theano in the works and will be released in the next update. And so again, in the interest of time, I won't dive too deeply into this right now. I'll show this hands-on tomorrow morning. But what it is a web-based interface that allows you to both set up, so ingest your tens of thousands of, millions of images. It'll create the database for you. You can select some of the pre-baked neural nets. So for example, the winning entries from ImageNet, right, that Academy Awards of Image Recognition from 2012, the one that led to that step change, and also Google's entry, which they published in 2014. We actually, package that with Digits. So you can download that, and Digits is open source. You can train it from the web interface, and there's obviously a web API associated with that, and it'll give you real-time statistics on the health of your GPU, the temperatures, the utilization. If it ran out of memory, well, then you need to tweak a few parameters and what those might be. And finally, once it's all trained, you can feed it some images that it has never seen before. And again, I'll show you this. You can get some pretty hilarious results, to be honest, because it's not perfect. You can feed it some results, and through the web API, you can see how easy you might be able to deploy this on something like Amazon or Google's cloud with GPUs, and just build a front-end app from iOS or Android. And so it scales pretty much linearly, which is fantastic, across GPUs. This is within a single server. So 1, 2, 4, if you're getting over 3 times sort of speed up with 4 GPUs, that's pretty close to linear scaling. And I'll just finish on this slide. How you would deploy it is you'd run it on some server hardware, probably much like I've got set up in the lobby there. And once you've trained your network to your satisfaction, you can actually then download out that model file. It's only a couple of hundred megabytes in general, and you can deploy that on much lighter weight hardware. So your phone, your tablets, I didn't forget about this. So I'm giving away a Jetson TK1, which is a Tegra K1, so 192 CUDA cores in 5 watts, right? So this is what powers the display in a Tesla electric vehicle. It was what powers some tablets and phones, and you can deploy your model on this. Right? You train it on the heavy-hitting GPU clusters, you deploy it in something like this. And there's no need to copy any of this down. We'll make these slides available, I assume. Yeah. There's an online course happening right now. We're 2 classes in. Unfortunately, they happen at 9 a.m. Pacific Standard Time, which is like 2 a.m. here. But they're all recorded, right? And so the first 2 have already happened. One of our engineers gets on, talks about it, and there'll be a live question and answer, as well as office hour session where you can ask questions that you run into, or for problems that you run into. And lastly, but not least, we also have some cloud deployed labs, hands-on labs. So you don't have to buy any hardware and set it up for yourself. You just sign up with your email there, and you have about an hour's time to have a play with the digits stack yourself. Yep, and there's some more useful links which will be shared with you. So that's it.